Good morning, everyone. Welcome to the Distinguished Lecture series. So it's my great pleasure to introduce you our distinguished speaker today, Professor Jan Stoica. So Jan has been a professor at UC Berkeley for since 2000, and he was my postdoc supervisor before I came here. He taught me how to do cool systems research, and more importantly, he showed me how systems research can actually change the world. So Jan is one of the most impactful and most successful researchers in systems and networking. And over the past 2 decades, Jan has been constantly leading and shaping the research field of systems and networking. So his PhD work on core stateless networking won the ACM Dissertation Award, and he proposed Chord, which became one of the most important algorithms in P2P networking. And he's also the creator of a series of amazing work in distributed systems and machine learning systems, including Ray, Apache Spark, Apache Mesos, and Tachyon. So these work have fundamentally changed the way how data is processed, stored, and managed, and has shaped the landscape of the current landscape of data analytics and cloud computing. And these contributions have been recognized at the highest level. So Jan is a member of the National Academy of Engineering in the United States. So he's an honorary member of the Romanian Academy, and he's an ACM Fellow. He has received numerous prestigious awards, including Mark Weiser Award, the SIGOPS Hall of Fame Award, and several Test of Time Awards. And besides academia, Jan is also a co-founder of several companies that are extremely successful. So including Anyscale, Databricks, and Conviva. So Databricks alone is worth over 40 billion, and thousands of companies are using it every day to process their data. And Anyscale is a key enabler behind OpenAI to train their ChatGPT models at scale. And moreover, Jan is also the director or co-director of a series of amazing labs in Berkeley, from AMP Lab to Rise Lab, and now the Sky Lab. So as a former lab member, I couldn't tell you how great these labs are for students to grow and to learn. Right? And as a supervisor, Jan has advised many students who have become successful computer scientists. And some of them are actually from University of Waterloo. For example, Matej Zahara, which is now a professor at UC Berkeley, did his undergrad here. And Mashaf Chaudhry, which is now a professor at Michigan Ann Arbor, did his master here with our department chair, Raouf. So Jan's current research focus is on AI systems. So today, Jan is going to share his insights on large language model systems by talking about several exciting projects he has been working on in the last 3 years. So please join me in welcoming Professor Jan Stoica. Thank you, Jan.
Thank you. Thank you for this great introduction. Very hard to live to the expectations, and great to be here. So today I'm going to talk about a few things. And by the way, when I give an advice to my students, I'm telling them, hey, you should talk about one thing, okay, and do it well. So I'm not going to do that. So I'm not going to follow my own advice. So I'm going to talk, and just to give you a context, I was lucky in the past 15 years or so to be involved in quite a few projects, open source projects. And during this talk, I am going to describe 3 of these projects, Ray, VLLM, and Chatbot Arena. And the way I am going to link them, it's like they actually create a kind of a stack. So VLLM is using Ray, and Chatbot Arena is using VLLM, okay? But they solve quite different problems. So from that perspective, there are 3 different pieces of work. So let me start with Ray, and this is the oldest project I'm going to talk about. It started a long time ago. It started, almost 8 years ago. And just to provide you some historical perspective, before Ray, we worked on other projects, including Spark, and Spark was about scaling data processing. So at that time, what the workloads we are looking to scale was big data, if you remember Hadoop of the day, and also classic machine learning, random forest, logistic regression, things like that, before LLM, before deep learning. And the target was kind of homogeneous clusters. Every node was more or less the same, has a CPU and some storage. Ray started 7 years later, and it targeted deep learning and reinforcement learning, so the new workloads at that time. And the target cluster become also kind of more complex. It was not only distributed, but heterogeneous clusters, including both CPUs and GPUs. To be more precise, when we started Ray, these are the trends. AI demands are growing quicker than ever, and clusters were becoming heterogeneous, and AI workloads in themselves, they are becoming more complex. Everyone sees this plot or something similar to this plot, which shows that demands in terms of compute of training the models that was on the y-axis, log scale, or on the x-axis is the time and is the size of these models, which increase over time, right? And if you do some fitting here, approximate fitting, and you get this kind of numbers, depends when you do it and how you do it. But in this particular case, the demands in terms of compute of training the largest models of the day was growing like 10x every 18 months, okay? And even if you look at the cost and the latest models, I don't have the plot here, I should have had it. If you look at, you know, GPT-2, GPT-3, GPT-4, everyone, and maybe GPT-5, so everyone is going, you know, every 2 years or so. GPT-2 was like $40,000 to train. GPT-3 was like between 4 and 5 millions, 4.7, some say. GPT-4 was between 60 and 100 millions. And it's expected like GPT-5 to be like 1 billion, between 1 billion and 3 billion. So it's kind of 10x even in terms of the dollars to train it. And of course, you need also to factor in the improvements in the compute. So, you know, in terms of flops, it's going to be more than 10x. So it's kind of triangulates. Now, at the same time, obviously, we knew that Moore's law, this was the cornerstone of the progress in computer science for the longest time. And that was improving the performance 2x every 18 months, right? That was kind of what happened. Of course, we know that Moore's law, you know, started to fizzle at the beginning of this century. And this is actually what is a CPU, what is a growth in the CPU performance. And then people start to come up with new things to bridge this gap between the capabilities of a single core and GPUs and TPUs and things like that, right? So this is, again, this is GPUs and DPUs, again, is like they are far more performant, but still the growth is around 2x every 18 months or whatever, 2 years, you know. So still the slope is very different. So still a huge gap. So that's why you had, now you need to deal with much more complex infrastructure. It's not enough only to scale it horizontally to have more machines, but you also have to have, you are going to have heterogeneous infrastructure composed CPU, GPUs, right? That's a problem. And then the workloads becoming more complex. And I'm going to give here a simplest actually workload, which is, you know, like it's from, you know, 5, 6 years ago. And this is a pipeline, the typical pipeline for machine learning, right? So what do? You get some data like logs of the users. You pre-process these logs, and the user, you know, this pre-processed data, you do featureization, you compute embeddings, and then you train a model, or pre-train in today's terminology. Then you fine-tune or post-train, and these boxes are very complicated now, okay? And then you serve the model, right? And you get more data and you iterate, right? By the way, before you serve, you do batch prediction, right? You try to figure out the new model on the past data, how it's performing before deploying it in production. So the main point here is that each of these stages eventually you need to scale, okay? And there are, like when we started Ray, and even until very recently, there are systems you can use to scale each of these stages in isolation. So then to build a pipeline, you need to stitch together these systems, right? All of them distributed systems. So what are the problems, right? So there are a bunch of problems. First, it's hard to develop. Why? Because each of these systems has its own API, right? Then it's hard also to deploy and hard to manage because it's hard to deploy and manage different distributed systems, each of them with its own semantics, not only about processing the data, but semantics about failures, recovery, and so forth. It's very complicated to have a reasonably end-to-end semantics, for instance, for the failures or recovery from failures. And it's also slow because in order to move the data, and if you have a lot of data in these cases between these stages, you need to serialize, deserialize it, store on this blob store, and things like that. So that's a problem, and this is a problem Ray solves. And Ray basically it's a general framework for distributed computing, and you can use Ray to scale all these workloads. And to make it easier to scale these workloads, we also have this kind of you'll see some libraries on top of it. But fundamentally, you need only one system instead of many. Okay, that's the TLDR. So now Ray has this part of the basis, which is a call core and a bunch of libraries, like I mentioned. I'm going to talk about Ray core, which is a distributed framework. And it's very simple. It has a very minimalist API. I'm not going to go through all of these. I'm going to show a few of them, part of some examples. And Ray is implemented what we called fast compute model. So what is fast? A stands for actors and T for tasks. So the reason Ray is so general is very simple. It takes this kind of the main compute abstraction you have almost in every language, which is functions and classes, and instantiate them, like function you can call remotely, a little bit like RPCs, and transparently. And classes, you can instantiate them remotely, but classes have state encapsulated with them, and they become basically actors, right? What, in all this language like Erlang or Orleans and so forth. So this is basically, you take these constructs, and you can remotely and transparently run those, okay? This is actor and task. In addition, you have this future abstraction. So when you are going to instantiate, for instance, a task remotely, a function remotely, when you are going to do that, you are going to get back immediately. You don't wait for it to run until the end. You get immediately back what we call a future, basically a reference to the result, to the future result. And why is that? Because this allows us, like we'll see, parallelism. Because now you can instantiate another task and another task. We'll see an example soon. And finally, is the shared in-memory distributed object store, which allows you to actually pass the argument a result by reference. Right? As you know, in many languages, like in your systems 101 or programming languages 101, there are two ways to pass, basic ways to pass arguments. It's like by value and by reference, right? Typically in distributed systems, they are passed by value, like RPC. When I call a function, I also send the value and I get the result, okay? But obviously, when you have large data and so forth, passing by reference has its own advantages. You'll see that as well. So that's pretty much what it is. So here is a simple example. This is a Python. If I forget to say, I'm going to say now, like the backend of Ray is in C, C++. The front end has multiple front ends. The most popular is Python, okay? So it's a trivial function. Let's say this function takes 1 second. And you call this twice with different arguments, okay? So it will take total 2 seconds, right? Now, let's say we do this with Ray. So first of all, in order to make this function and we call it a task, we add this decorator, ray.remote. And when we call it, we do f.remote, and then we do get. Let me tell you what happens here. So let's see, go line by line. So when you call this f.remote, what happens under the hood is that, so this program runs on a driver, think about the main program. You submit a task for F to the system, okay? And the system is going to, Ray, I'm talking about, Ray is going to decide where to schedule this task. But even before scheduling it, it's going to return you this feature, right? The reference to the result. It's not the result. So the function call, it's asynchronous, gives you back the reference immediately, which allows you to call the next function, f.remote, so create another task, right? So now at this point, you submit 2 tasks, right? And the system will figure out them or to schedule, and then to run them. And in this case, because there is no data dependency between the tasks, they are going to run in parallel. Now, in order to get the results, you need to do this read.get on these futures, right? And f.remote and it's asynchronous, returns immediately. Obviously, read.get will be blocking. It has to wait for the results. So now this f of A and f of B, eventually they are going to be scheduled and they are going to run and they are going to produce the results. And when they are going to produce the results are going to be sent to the driver which will get the results and will do whatever, print them or something like that. So that's what it is. Very simple. Like I mentioned, it's when you have classes and you instantiate classes, you get these actors. The same way you add the ray.remote decorators and you add .remote or you instantiate the class, which becomes an actor, and then you invoke method on that class. It also, one thing, remember that Ray was designed to handle heterogeneous clusters. You can specify, for instance, number of CPUs, GPUs for your class or tasks, right? Requirements, resource requirements. So these are task and actors. Now about shared memory. So it has a shared object store in memory object store. So actually this is distributed object store. And here it's an example in which a function G, as the argument of function G, it's a result returned by a function F. So it's G of F of X, basically. That's what it implements. So first of all, we call f.remote, and f.remote here is going to return again the reference to the result. And the reference to the result will be passed to the function G. So return from function on, or from function F, okay? So you are going to instantiate now g.remote as a task, okay? So again, now you start to execute, and now there is a dependency between G and F. So G will wait for F to finish, and F, when finishes, it pushes this result in this shared object store, and then G has a reference to the result, and when the result X is ready, is going to be transferred to the node on which G runs, and G is going to consume now the input and is going to create the result, okay? Okay, so simple. Now, the main point to notice here is that X is transferred only once between node 2 and node 3, which is trivially optimal because F, in this case, runs on node 2 and G runs on node 3. Okay. Now, let's see if you were to implement this using RPC, what will happen is that you call, it's again, with RPC is by value. You pass the input, you pass the argument, and you call the function, and you get the result. So basically, when you call F, you are going to get the result back, and you have to pass the result to G, and then G is going to send to node 3, where G is going to run, and then G will get its own, will compute the final result. Why? So, but the main point here is that now this X is moved twice, one from node 2 to node 1, and then from node 1 to node 3, right? So less efficient. But we know that, right? That's why we do the, when even for a single machine, that's why you're passing by reference to avoid copies, right? When the results are very large. So no surprise here. I just wanted to say that it's applied also to in distributed systems, right? So the Ray ecosystem, just to remind everyone, is like this Ray core, which is a unified computing framework for distributed application, which has implemented this kind of fast compute model, and which has task, actors, a shared object store, and futures as the main constructs. Okay. And then you can build really virtually any distributed application, but in order to make it easy to implement some workloads, to support some workloads, it also provides some libraries for data processing, tune is high parameter tuning, serving, and reinforcement learning. This is RLE. Okay? Like everything, right? It's like also Spark in the days or Python, right? In order for the most popular workloads, it provides libraries. Okay? That's basically about Ray. And it's quite successful. Many companies use Ray now to implement their AI and ML infrastructures and platforms, ML platforms. Initially, they implemented these platforms by stitching together the systems. Now, the second generation of platforms, many of them use Ray. Probably one of the most impressive use cases is OpenAI, the train GPT-4 and so forth on top of Ray. And other large language models or what these foundation labs are using Ray. And, it's quite successful open source project. So now, there is something else, changing, right? For the past several years. So what changes is that, unfortunately, we have this large language model, and the cluster heterogeneity has increased, right? It's not only we have this kind of separate GPUs, and you do like you're used to train data parallelism. You have a model on one GPUs, and then you just kind of shuffle the data to build the batches to feed it in. You have model parallelism, so you have much more integrated, and then you have now TPU pods, right? It's like or GPU pods where you have a bunch of GPUs which are very well connected, right? So we are actually one of the most biggest trends today. You have this rapid transition from the CPU-centric to accelerator-centric world, right? You should look no farther than valuation of NVIDIA as a proof point for this, okay? So, but this is what happens, and I think that is one challenge. You need also, to recognize this trend and, probably have changes in curriculum or something like that to do it. And now Ray is very dynamic and flexible, like Python. You think about, you can do whatever you want, but it has high overhead for small tasks. Again, like kind of Python, everything which is very dynamic has a overhead. You need to pay the cost of RPC, the cost of dynamic memory allocation. It's difficult to efficiently support peer-to-peer protocols like RDMA nickel, right? I've mentioned about this direct communication between GPUs. Requires upfront resource allocation to all peers to avoid the deadlock. So you need to be careful about a lot of things. So let me show you what are the challenges. Here it's a simple example, a very simple example. So basically you have two tasks or actors in this case, and basically just trivially, you increment a value. You have a value, you pass to the first task or actor, in this case A, which will increment it, which will pass to B, which will increment it, and then return back the results to the driver. So you do something, if you have RPC, you do something like that. You pass 1 to A, it's going to return 2, then driver pass 2 to B, and it's going to return 3, right? So this is what it is. So what Ray is doing to implement this, right? So first of all, the driver is going to put the initial value in the shared object store. And then this is one ref is a reference to the value, and it's going to pass the reference to the task or actors, whatever you are going to use. Now, and A is going to pass the future to ref, it's its own result, back to the driver. And then A, when it runs, is going to read one value and is going to create the result 2. Now, driver, once it receives these 2 ref, the reference, the future of the results of A, is going to pass it to B, and B is going to pass the final, the reference to the final result 3. Now, B is going to read 2 and create 3, and then you send it back the result to the driver when it's ready. All of this happens. So what happens here, if you look from the point of view of the driver, you have 2 data copies, right? And 6 RPCs, right? You just count the thin arrows are RPCs, just control like RPCs. And then you have also dynamic memory allocation. By the way, I forgot to mention to you, in the past, there are 4 memory copies, 4 data copies between the driver and the rest of the system, right? So here you have only 2 memory copies to the driver, which is good if you have huge amount of data. If the data is huge, the control doesn't matter, right? But if the data, you have small operations, now the control, you are going to pay a price for that, and memory allocation and everything. So this is a problem we try to solve, right? And this is what is called this accelerated dynamic acyclic graph, ADAGs. We actually call them compile graphs now. And we wanted to run this task of between 1 and 10 milliseconds with less than 1% overhead. And we also to have GPU to GPU communication, which is very quick in the order of less than microseconds to set up the communication. So fundamentally, what do you do here? If you have a repeated computation, like training and things like that, you know that. So what you do, you kind of compile that kind of graph in the sense that you try to set up the graph and not pay the dynamic overhead for each invocation and everything, right? And you allocate resources in advance, and you declare the peer-to-peer communication between GPUs. So this is what will happen. Ideally, if you use this shared memory object store, this is what you should happen, right? Little or no control overhead. Get rid of the RPC overhead. Also, I'd avoid dynamic memory allocation. So here is what happens. Now you can construct this DAG. So basically, you take A and B, and A gets the input, then you send the output to B, and then B is going to eventually to send the results back to the driver. So you declare this graph, right, already. And then you compile it. What does it mean to compile it? Is that you are going to start these actors, and these actors are going to run in a loop to get the data and produce the results. You also are going to pre-allocate static buffers, and you can reuse across multiple executions. So you set up everything from the beginning, and now, right, once you compile it, you execute the entire graph, and the entire graph is going to do what you want, right? Because you pass all the references, everything from the beginning, because this memory allocation is static, it's not going to change over multiple iterations, right? So that's what you do. So it's very fast, and this is what you do, like, for instance, for GPU to GPU communication. Today with Ray, things are pretty complicated because what you need to do it, if you want to send a tensor from GPU 0 to GPU 1, you take this tensor, you are going to copy to the shared memory, which is a RAM. Then you move it over slow network to the other node, and then copy back in the GPU memory. Instead, with compiled DAGs, you create directly a graph between GPU 0 and GPU 1 to transfer the tensors, and you transfer it directly. You can specify what is a transport, in this case, nickel. Okay? That's pretty much what it is, right? So basically, you compile. If you have repeated execution, you are going to make it static, right? You compile in a static execution DAG, and you pre-allocate the memory, right? Exactly what a compiler is doing, right? More or less. So there are many application examples about with Ray, and I just want to give you a few of them. This is online inference or batch inference. You read some data, you do model inference, and you write. And what you gain a lot here is because from you can mix different resources. So for instance, read and pre-processing and post-processing can be of the data can be done on the CPUs, while inference can be done on the GPUs. Okay, so mix and match. And by doing so, you can reduce the cost by 10x compared with systems which cannot do mix and match, and they do everything. In this case, they have to do it on GPU. You can do fine-tuning, the same. You can do multimodal search, similarly, and embedding computation. It turns out that right now, you have to mix this heterogeneity is increasing at the level is that even for inference, you may want to use different GPUs, right? Or CPUs and GPUs. Like, for instance, for pre-filling, to compute the attention from the prompt, you can use CPUs, and then one prompt at a time to generate, you can use GPUs. For multimodal, for encoding, decoding, you can use weaker, lower grade, cheaper GPUs. And for running the transformers, to the inference of the transformer, you can use expensive GPUs, right? High performance GPUs. So a lot of things, it's just increasing quite a bit. And if you are talking now about pre-training or post-training in particular, it's very complex. So that's kind of host array, okay? So so next, it's about array was this kind of distributed framework for distributed compute running on heterogeneous clusters, targeting this scaling AI workloads. The VLLM, it's one particular workload going up in the stack, and it's about serving inference, right? As you know, inference becomes more and more important right now with the large language models. Why it becomes more important? Because large language models are more general and more general purpose, so they can do more things. So you do that as an inference time, right? It used to be that for every kind of use case, you need to train a model in the previous generation. But now, because you have very general models, you don't need to train them all the time. So this inference becomes more important, right? And you can see with this, you heard about test time compute. Test time compute is doing even more at the inference time. So anyway, now the problem with this one, at least when we tried, this was much. We started last year this project. It is very expensive, right? You just get a few requests per second. Even at that time when we started, you have, I think it was A100, yes, or even H100, which H100 is still probably the best NVIDIA has today because Blackwell was delayed until next year. And even for Llama 13B, which is a small model, 13 billion parameters, it's just a few requests per second. So very expensive. Now, between when they were launched last year and this year, the model inference decreased by order of magnitude, okay? And this is one technique which was used to get these improvements. Now, everyone knows about this large language model, how they work. But just let me remind you, it'll take me 1 minute, because it's important to understand the problem. And if we understand the problem, we understand the solution easily, right? So you know how this works, right? It's basically you predict the next token based on the previous tokens, right? It's access into artificial intelligence and you are going to predict using this attention mechanism, the next one, right? The next token, and then you use all the previous tokens to predict the next one and so forth. So the main point here, you have a dependence between the next token you are predicting and the previous ones. So what is the problem with this? The problem with this is that it's sequential. And GPUs are very, they get all these kind of flops from parallelism. Okay? That's the problem. And then you cannot exploit GPU parallelism. So utilization of the GPU for this kind of computation is low, right? So low throughput, high cost, okay? So what is the solution, right? You cannot get parallelism within the same query. What do? You have more queries, right? That's obvious. So you have more queries at the same time you process, and now you get parallelism across queries. But then you run out of memory. Why you run out of memory? Because remember, for each query, you need to keep all these previous tokens in memory. And it's not only tokens, it's kind of this embedding. So this is how, for a 40 gigabytes A100, this was state of the art when we started 1.5 years ago, more, If you have 13 billion parameters and you use 2 bytes per parameter, you have 26 gigabytes. So it's 65, this is parameters. And then you have this KV cache. The KV cache, you keep this kind of embeddings, the metadata for the tokens, right? This is KV cache, 30%. And others, this other activation and things like that. Again, many things have changed since then. The number of parameters now are, like the amount of memory you need for a parameter is much lower because you need quantization and all of these things. But the main problem is, again, this is, you need for each query to put this prefix in the cache. And each token embedding metadata associated with each token, it's 1 megabyte. Okay? And as you probably know, people also now want longer and longer context, right? That's one thing you look when they announce a new model, they say, oh, there's a context now. It's like, but Google Gemini is like having 1.5 million, okay? So one request can have several gigabytes, okay? So that's what it is. Now, when you look at that time, about how the system handles the memory, they use contiguous allocations. Why contiguous allocation is kind of makes sense because you just, you are going to have this kind of request and you are always for the next token, you are going to use everything what was before, right? So fundamentally you say, oh, I'm going to allocate a contiguous memory for all this, for the entire request, and that's all. And it's also easy, right? So that was a problem. You need to allocate. Now, it turns out, and then you have a lot of fragmentation. So you have internal fragmentation because you do not know how long it's the output, right? Okay. So actually, you are going to have different prices if you want 2K or 4K. This was there early on, right? So that's clear one, right? The other one, it's you also have, you need to have this reservation. So what does it mean, this reservation? Is that, say, even if you know exactly how long is going to be output, you allocate that space, right? So at the end of the day, you are going to fill all the memory you allocated with the tokens of that query. The problem is that you do it one by one. So it takes some time to use all this memory. So that is could have been an opportunity to use the memory for other requests, right? Right? Because you allocate token by token, right? So that's kind of what is this kind of reservation. And of course, you have external fragmentation because not of these requests, even if you pre-allocate, is not all of them are the same, right? Some of them will be 2K, 4K, and things like that. Okay? So you have all of this fragmentation. And this was pretty bad. So this is what you have, just to be, the main takeaway from this plot is that this green stuff is how much you allocate from the entire memory, and the rest is almost wasted because all of these inefficiencies. So, and this was, you know, state of the art back then. And the last one, this says if you are Oracle, if you know how much you need to allocate to each request. This is 38%. So what is the solution here? The solution here, we know from system, we have these similar problems before in operating systems. Memory management, you remember, you know, internal, external fragmentation. How do you do that? Use this kind of paging, virtual memory, right? So that's what you do, like with the processes. So this is what we do here. It's again, application level kind of virtual memory for inference. Right, that's what the TLDR. So you have KV blocks instead of pages. Pages, the most smallest unit is a byte or a word. Here, the smallest unit in one of these blocks is a embedding associated with a token. And you have here on the logical KV space or virtual one on the left-hand side. On the right-hand side is a physical KV block. So all the applications are going to be actually unchanged because what they see in the logical space is still a contiguous region of memory in this space. And then you have a table which is, maps the tokens from logical space to the physical space. Right? And the key here is like it's a little bit, you optimize a little bit for this application because here for each block, because you allocate only append to a block, a new token, you have this field, you say the second column tells you how many tokens you filled in the block. Like for instance, in this case, in this block 1, you have computer scientist. So you filled only 2, right? The block size is 4 in this case. So when you are going to run to generate the next token, you are going to add it in block 1, and then the next token also add it to block 1. Now you exhausted block 1, and you are going to allocate another block, right? But again, the blocks are fixed size. You allocate anywhere. You don't have external fragmentation. You have just a little bit of internal fragmentation. And there are many cases. And then you can also, like in operating system, if you can share, right? You can share pages, right? I can share tokens here. And for instance, here, parallel sampling. There are techniques in which you are going to generate for the same input, you are going to generate different outputs because, you get the next token with certain probability, so you can pick the top K, and then you try to pick the best answer out of this, so you share prefix in this case. Also, you can share the prefix in a dialogue, right? It's a multi-turn. In a multi-turn, you feed the LLM with all the previous conversations. So it's a lot of prefix sharing there. And the memory, no external fragmentation, like I told you. And the improvements are massive, right? Very simple technique. It's 25 to 5x. And this translates higher throughput and almost can translate in reduction of cost, right? And these are some numbers. At that time, it was this TGI from Hugging Face was the most popular inference engine. And you can see that VLM is throughput, higher, better. And you have, a few times improvements, okay? So that's what it is. Higher throughput, lower cost. More requests on the same hardware. So now, just going a little bit in analogy, this is also always fascinating. You can use these techniques which are before, but when the problem setting changes, the solutions start to change a little bit as well. This is cool. So what are the analogies? Like what are the similarities? Like I told you, OS pages are the KV blocks, okay? Reduce memory fragmentation, the same reason. You can share the blocks like you share pages. This is similar. What are the differences? the eviction, right? Now, eviction here, right, for instance, in virtual memory, you do eviction typically at the page level. Here, when you do the eviction, if I am going to miss one of the token before, the other are not very useful. So if you evict, you can evict the entire request, the entire prefix. Also, the other question, it's about when you bring it back, right? When you need, with operating system, you put in a swap file and you bring pages back when you need them. It turns out that here, actually, in some cases, it's faster to recompute. Here, the swap space, natural swap space will be on the CPU RAM, right? Because it's a lot, right, on the same machine. But here, it's like actually in many cases, because GPU has so much parallelism, it's faster to recompute all these tokens. Okay. And there are many other things. We've done a lot of other work here. It's much more sophisticated now, but I'll be happy to answer questions. This was, it's very successful. Right now, it's probably the most popular open source inference system. It's used by many, many companies, cloud providers. And the page annotation as a technique, it's also used by basically every other inference engine, not only VLLM. By the way, this is techniques I mentioned to you. It's called page attention. I'm not sure it was one title. Okay, so this is the second one, right? So VLLM works on top of Ray, where Ray helps VLLM when things get distributed. Like for instance, pipeline parallelism. When you have to divide a model on multiple GPUs, and then you need to feed, in order to compute the next token, you need to feed the outputs. You divide it by layers. There are many ways. So you do tensor parallelism, right? Horizontally divide or horizontally divide these kind of models. And then you need to handle the resource allocations, the communication between these GPUs. And this is where Ray is a default engine to do that. Finally, the last one, Chatbot Arena, and this is about LLM evaluation. Okay, and this was an interesting project. It's very different than what I've done before. And what was the problem? So, and I'll tell you a little bit later what was the progression to get to this project. And obviously, we all know benchmarks are very important, right? Dave Patterson is used to say this kind of, for better or worse, benchmark shape a field, right? And obviously we have ImageNet and all these kind of very celebrated benchmarks in AI, right? Which are used to put actually this deep learning on the map. Remember that the fact that it did well on these deep neural networks, they did achieve performance on ImageNet, which are exceeding the other classic solutions performance. It was the first time really people started to pay attention to deep neural network, and then they also match the human accuracy. Okay. The problem with this large language model is that they are extremely hard to evaluate. And the evaluation is expensive, it's unreliable. Let me give you an example. Say this prompt, okay? Develop a Python program that reads the text files under a directory and returns top 5 words with the most number of occurrences in these files in this directory, okay? You ask the LLM this, okay? And you get these answers. Which one is good? Which one is better? Okay. It takes some time. Okay. Okay, and you say, okay, this is code. Let me try this one. Photosynthesis, it's a vital process for life on Earth. Could you outline the two main stages of photosynthesis, including where they take place within the chloroplast and the primary inputs and output for each stage. Right? Biology 101. Okay? I'm not asking you to give the answer. I'm asking you to say which one of these two answers is better. Okay? Not easy, right? Okay. Now, the other problem I said is they are unreliable. And that was because data contamination. Because these large language models, they are trained on everything. As you know, one of the biggest problems today is like running out of data. Talking about synthetic data, and that's why each of these foundation labs, they pay a lot of money to get new data sets, right? Proprietary, like to improve their performance. And this is very early on. It's like this kind of tweet. I suspect GPT-4 performance is influenced by data contamination, at least on code force. Of the easiest problems of code forces is solve 10 out of 10 pre-2021 problems and 0 out of 10 recent problems. So solve everything before the cutting date of the data used for training that model, and nothing, after that. Then it was this other, I don't know if you remember this. It was because it made some wave. It was this paper coming up from MIT claiming GPT-4 can score 100% on MIT's CS curriculum with the right prompting. That's pretty good. It turns out that that's not the case. Later become, what this disclaimer, it's like zeros contamination. And of course, GPT-4 was trained on all of these kind of exams, right? If you take that into account, then the accuracy is still good, but decreases to 58% from 100%. Right? So you need to be very careful. So let me tell you about our stories of how we do get into this problem. So in February 2023, Facebook, if you remember, it seemed like an eternity, but it's not that far long ago, releases this Llama open source. And then we did some fine-tuning of Llama using this data, which was called ShareGPT data. So ShareGPT data was this kind of site where you can share the inputs and outputs from your conversation with GPT-4, right? And it's supposed to be open. I think in the meantime, they changed the license and everything. But at that time it was open. And it was not 70,000 conversations, not much. But they were very high quality because people are not going to share, their bad they're only share the interesting conversations, right? So we do that. And we call this model Vicuña, and for a while, it was the best open source model. But our problem when we release it, how we are going to evaluate it, okay? And the typical evaluation you do to humans, right? Is like you use humans, a bunch of graduate students, buy them pizza, do some evaluation. However, the one thing what we realized, actually, one of the students on the team is that why not use GPT-4 to evaluate? GPT-4 was released only 2 weeks earlier, right? And this was kind of the genesis of using this LLM as a judge. Okay, so that's what we use. Okay, so use that. And when you look at that, you remember about this Python program? Which one is good, better? Okay, so GPT-4 answer is that, well, assistant A, you see A, B, right? There's 2 choices. They have similar answer, but A does not handle case sensitivity or punctuation. Okay, makes sense, right? So it seems, oh, it's pretty good actually, right? And for the one, it's again, assistant A makes a mistake confusing the two stages, the input and output from the two stages. He says that the inputs from one stage actually are from the other stage. You look at it, okay, makes sense. So that's kind of was our, now. So this is LLM as a judge. We use it, but still you want to have, again, remember, this was the first time we used LLM as a judge. People, or, it's obviously legitimate questions, right? Oh, you have some examples what's working, what about in general? So you also wanted to double by some human evaluation, right? This has a ground truth. Actually, after all, it's for humans. These answers are for humans. So let's see how they are, they are the ultimate arbiters. But how you do that? And this is what is a result of this chatbot arena we build. Now, ideally, if you want to evaluate, I'm going to have a question, and I'm going to get an answer from each LLM, and I'm going to rank them, right? That will be ideal. However, it turns out this is hard. And ranking any choices is very hard, okay? Actually, it's easier to pick best of n, but even there, you remember, this is an interesting book, The Paradox of Choice, right? Having multiple choices, it's a lot of stress on humans, right? It's like, but the best one, the easiest one, it's I give you only two choices to pick one of them, right? I'm not saying it's easy, it's the easiest, right? And you cannot do less than that, right? I need still you to decide between two choices. So this is what it does. Now, even that, down to the next question, then how you are going to organize this kind of comparison between two LLM at a time. And there are a few ways to do it. One, which is it's a complete and probably the most accurate, is tournament, right? For you, like they are soccer fans, like Premier Leagues, right? You have a championship, every team plays with every other team, right? So then you have number of wins and losses, and ties, and you have a table. Now, the problem with this is accurate, but it's hard to scale. It's n squared. And it's not only that. If a new model comes in, it's hard to add it up to all this, right? Now, fortunately, we solve this problem in other sports. And we have this concept of ratings. The most common, one, it's chess, right? You have this kind of ELO rating, but it's not only in chess. You have in many other sports. You have in tennis, ATP ranking. And even when you compare different teams internationally, not all of them play with everyone else. In soccer, cricket, and so forth, the same thing happens. You have this one of this rating. So this is what we build, and we use kind of ELO-like rating to do it. Right? So then we develop this system in which basically this is a chatbot arena, and you ask a question, and you are presented with two answers from two anonymized and randomized large language models. Okay? And then you say A is better, B is better, tie, or both are better. Right? And this voting is going to compute this kind of ratings. And it's the latest one, right? As you can see. The arena score, which is a version of ELO score, and the best one, GPT 4.0, a one preview is a little bit lower. And the first, the open source, the top open source one is Llama 3.1. Okay? That's what it is. We accumulated a lot. Right now we have over 80 million prompts and over 2 million votes. The votes are this is by time. The top, do you know what is the top one? This is all the rumors, which was true, that OpenAI is testing GPT 4.0, the strawberry was called back then. So people kind of found out somehow, and then they come to see to find it, to test it. You can do it again. You don't need to vote. Actually, for the main chatbot arena, it's only these blue things that are votes between 5 and 10%. But these are used actually to generate the funnel for the voting, right? It's like people come here because they can use some of the state-of-the-art model basically for free. And we have a lot of, I should have added, it's actually have a lot of diversity in terms of categories, coding and reasoning, problem solving, and this is again log scale. This is different countries. So English, Chinese, Russian is the next one. Maybe not surprising. Okay. Now remember, so we have this kind of results from humans. By the way, the results we get here are high quality. Why are high quality? Because two things. One, people try to solve their own problems. Again, remember, it gives this for free. But the second one is that people evaluate the answer to their own questions, right? Which is supposed to provide you higher quality labeling because they have the context, and then some third party, even if it's expert, evaluating a third party question and answers. But anyway, so going back to, and I'll be done in 2-3 minutes, is that it's still, again, you have this LLM as a judge result, and you have, on the other hand, you have these results from chatbot arena, from humans. And ultimately, you want to reconcile those, right? And this is what we did. And we did this systematic study. And here what we found is that the limitations of this LLM as a judge, using the LLM to judge, like I shown you before, are similar with humans. Because they exhibit position bias. They tend to assign a higher score to the first answer, right? Again, the way you ask this LLM, you say, hey, imagine you are going to a teacher and you ask this question on the exam, and one student gives this answer and this other student gives the answer, grade each of them from 1 to 10, right? Something like that. Verbosity bias, they prefer longer answers. Self-enhancement bias, prefer answer from itself, of course. And limited reasoning, not as good as grading math questions, okay? It's kind of very similar, okay? And of course, you can account for some of those, right? Like, for instance, position bias, you randomly, change the position and so forth. Now, but the one thing we look at is that the agreement fundamentally between a large language model and a human, and between two humans, right? Because humans are not consistent either, right? And what we ended up actually is a level of agreement, between the GPT-4 and a human expert, in this case, 85%, right? In 85% of the cases, they agreed, right, on the answers, which answer is better for the same prompts. And human to human, 81%. So it's pretty much in the same ballpark, okay? So the one of the most interesting things here and satisfying is that we are seeing right now early on this, because these frontier labs models of companies, many of them, they try to evaluate their model before releasing it, right? We release 20% of the votes. We don't release everything to try to avoid as much as possible overfitting. And we also have Arena Hard, which is prompts, harder prompts. What are the harder prompts? The harder prompts are the one which increases the distance between the strong models and the weak models, right? Easy question, everyone answers, right? What do you do to differentiate between students? Hard questions, right? The same here. And we have a lot of evaluation. We have new evaluation, we have image evaluation, is Vision Arena. We have one for copilots, right? You can there is an integration, collaboration with people from CMU, which basically, you have an integration in VS Code. And instead of getting only one suggestion, you get two. So you can pick which one is better. Red teaming, this is trying to fool the LLM to say something bad. Rep chat, basically here, this is repository chat. Basically, it's like you can pass, you give your GitHub repository the link, and then you can ask questions about your code, including how to fix this PR, which is pretty cool, okay? So in summary, I think that all of this what I've shown you, everything is open source, obviously. And for Chatbot Arena, I mentioned that we are releasing 20% of the bots, but all the stack we used to run, it's open source. All the analysis tools we use are open source. And obviously, when serving the model of this open source model, it's using VLLM, which runs on top of Ray for large models. And I'm still optimistic about the open source, even this language model, despite all this narrative. And I talk about these three projects in different layers, very different layers of the stack. Ray is for scaling and productizing this AI large-scale AI workloads. VLLM for high throughput, LLM inference, and then Chatbot Arena, which is basically application level artifact, and it's about how to evaluate LLMs. But still, we are, I believe, very beginning and very excited about things to come. Thank you.
Great, time for questions.
Thank you so much. I have a question about your first slide. You showed the trends, and the best of GPUs was still underneath everything else. Even if you do the best job in designing the best distributed system, it would be as if it's doing it locally. And it seems like the GPU growth is not meeting the growth in the models. So where do you see that going?
So one thing we are looking at, actually, I didn't have that. Let me put it this way. So one thing, is like, we are looking actually what happens if the GPU continue to increase and the model size stops. And this was for Palm, not for kind of GPT-4. Palm was, I think, 500 billion parameter or 600 billion parameters. And we are looking at that, and we are looking at that, assuming that every 2 years or so, you are going to get 2x improvement in the performance of the GPUs. It will take 19 years to run that on the GPU. So I think for the foreseeable future, you are going to see a continuous push at all levels. But on the infrastructure, it's again, GPT-5 is like 1 billion. You hear about Microsoft and OpenAI talking about $100 billion clusters, right? And the reason for that is that, still people believe that these frontier labs is like, and even countries, they cannot lose this race because whoever is going to win is going to have a huge advantage, right? That's why it's so big investment. So for a while, this will happen. Now, at the same time, there's a lot of improvements, efficiency, right? 10x, maybe, a few times, every year. But people just absorb this performance and still scale the compute, right? Now, for simple things, if you want, maybe for more practical applications, you can use this kind of smaller models. You heard about these smaller models. They are performing very well. Now, these smaller models, and this was one of the developments, which I was, personally surprised about how well it's working, but they are the styled models. You need to have very large models to teach these small models, right? So they are not coming for free. They are not like you train the small models from scratch and you get a good model, right? So you still have this kind of large models to do it. So I think that, and then it's like you want always to reduce the cost, but if you want to always to reduce let me put it this way. So the fundamental way, right, that you get this kind of improvement in performance for the accelerators is specialization, right? You narrow the workloads you are going to support, you can be smarter, right, about what to do it, right? And that way the flops improvements grow in general faster than the memory, because the flops you can, the compute, if you narrow you do really say only for transformers, to support transformers. You can do a factor of 10x better, right? Because I can put all this optimization in silicon, right? Something like memory is harder. I still need at least one transistor to store one bit, right? So you have this kind of specialization, but the specialization means heterogeneity, right? Because now I need to do for different things, I need to do different chips in order to bring down the cost, right? So I do think that heterogeneity and distributed heterogeneous systems are here to stay for quite a bit.
Hi, Professor. My name is Nima. I was wondering about the LLM as a judge. Would there not be a convergence in the distributions of answers based on what is already the existing best models that would kind of be passed up as models get bigger and bigger and trained on the best answers given in the arena?
So the question is that which models you are using for judges?
Yeah, I mean, you said at the time you used GPT-4 in February 2023, which was the best model. So I guess if more models are being trained on the preferred answers from GPT-4, would there not be a convergence in, I guess, the distribution of the answers that I guess...
Right now, you are not allowed to do that, by the way. You cannot. It used to be, this is ChatGPT, when we use ChatGPT, but right now, you are going to violate the license of OpenAI if you do that. Now, I'm not saying people don't do that, but you are not allowed to do it, right? But again, your question, it's very valid on, if everyone is going to train on GPT-4 input outputs, then yeah.
I guess I'm asking if it's an issue right now. Is it like an issue right now? Is like a problem? Like, is there like a convergence in the answers for most of the models based on, I guess, the previous best versions of them?
I think you have more convergence, probably not necessarily because GPT-4, but because something like Chatbot Arena, if you want to do well on this leaderboard, there are different things. There are things which are like style matters, like humans, right? It's like, so we try to factor out the style. So there are things like that. But but it's not as bad, because you can actually, there are systems right now trying to get better result and better accuracy, where GPT-4, like, you can ask something like GPT-4, this is a prompt, provide different answers. And then you ask GPT-4, which one is better? Because that kind of change the prompt and it change the answer. So even in that case, I don't think it's that bad. But yeah, it's a concern, always a concern.
Okay.
But great. I think it's more concern because the benchmark are much more serious concerns than, and as you can see, is like, if you see here, it's actually, and if you look at that, if you look at a leaderboard in the Chatbot Arena, you can actually have different Actually, let me see if I can show you. You can have, for different workloads, you can have, for different categories, you have different ranking. So it's not only one model. You see? Okay, so this is overall, right? But if you look at, for instance, you do coding, right? You'll see that the difference, there can be differences, it will take some time. You see some of them are, you see some variations, right? Like for instance, for coding, O1 mini is the best, right? And ChatGPT 4, which was best overall, is not as good. And I don't know what other things you have, but yeah, longer queries, or I don't know, English, what you'll get. Anyway, yeah.
I guess a really quick follow-up question then. You said the bigger issues, the benchmarks themselves. What's wrong with them right now?
People are trying to, it's like Patterson was saying, is a benchmark shape of field, right? It's like, if you remember, spec int and spec fp, right? It's like for the processors and computers, right? And I remember that I'm saying, spec int, and this is what you're doing, but on real workload, right? And on Excel or whatever, we are doing much better. It's unavoidable.
Thank you.
Hey, Professor, thank you for the wonderful talk. My name is Patrick, and I have a question about about you said like in continuation of the first question, like you said, there is like big gap between the current like capacity of the hardware and then also the model size. And then we are having some optimization in the software level. But do you think that there gonna be that gap is like achievable to narrow it down using our like software optimization that we currently have, or do you think that we need a new breakthrough in terms of like hardware program? Sorry,
I didn't get the last part.
Oh yes, do you think that the gap, narrowing down the gap is achievable? The hardware and then the model size, is that gap would be achievable to narrow down like in the future using those like software optimization and hardware optimization, or do you think that a new breakthrough in terms of like hardware programming, like outside of like currently NVIDIA's like SIMT model, or like, sorry, yeah, it's just little.
So I think it's again the gap. The gap will not get closed anytime soon, I think. Okay. It's again because it's a race, and people use the fact that there are algorithms efficiency improvements and the fact that maybe there's a level of training and inference just to build bigger models sooner, right? It's again, it's like, it's a race, right? Like people believe in this AGI, whatever it is, right? And they are going to try to be there first, right? So for them, it's just, I can get there faster. But they're always going, like for the foreseeable future, they're going to spend a lot, right? I mean, it's like Sam Altman is talking now about trillions. I mean, right? And look at the history, right? That's what it is. Put themselves, if you have the resources, what you are going to do, right? Of course, it's a competition between some companies with very deep pockets, right? So I think that will happen. I don't know what will happen in 5 years or whatever, but for the next few years, it will be. Now, there are all of these things actually, like that the main limitation actually, it turns out is going to be power grid, right? The power. And it's more kind of prosaic logistics, how fast you can build these data centers, how fast you can improve the power grid, right? Even if you go to nuclear energy, it's going to take years to do it. That's kind of the big limitation, right? But this is the way people are thinking about. They are thinking about how to remove these other limitations to scale faster, right?
Thank you.
Hi, thank you very much for the very enlightening talk. So I have a question on the last bit of it, which is the benchmarking part. And so I'm a bit worried that what you're evaluating, you're not evaluating, maybe you're not evaluating the correctness of or which one is better, but rather than which one the user likes.
Yeah.
And the user may completely mistaken, like doesn't have the true answer and could pick, the both answers could be completely wrong. So I'm not sure, because benchmarks typically are like the ground truth. This one is better than this one in performance or in quality or stuff. But this, depending on the users, is a bit more tricky. So I don't know what's your idea. Yeah, feedback on that.
Yeah. So there are multiple answers to that question. One answer is that, at least for this chat bot products, this is what companies want, right? It's about people preference, what they like most, right? Period, right? So from that perspective, you measure what you care about. The second thing, like I mentioned, though, is that nothing is perfect, but you tend to get better and better data if people who ask questions evaluate the answers. Okay. We also try to account for the stylistic differences by rewriting the answers to try to account for that. I think statistically you can account for that as well. So if you have enough data, right? Because you can rewrite, right? I can ask, okay, this is an answer from Anthropic. I ask GPT-4, can you rewrite this answer without changing the meaning and things like that, right? And the other way around, right? So you can do that. But always, it's not perfect, but fundamentally, at least the LLMs are not perfect. The natural language ambiguity, it's part of the game. So, and of course, if you have problems, like discussing earlier, if you ask that system, depending of what your question is, right? If you ask, oh, solve this equation, then it's easy, right? It's like it's working or it doesn't work, right? So it's a large variety of things you can do, and a large variety of tasks you can apply different level of specifications and verifiability. Yes.
Well, thank you for the excellent talk, Professor. I'm interested in learning more about how LLMs are being evaluated currently. Chatbot Arena does for quality of the answer, but in terms of, say, the compute intensity, at the very beginning, we had a chart about the flops. I'm interested in, say, with sophisticated computation graph compilation libraries like VLLM, how can flops be calculated, across increasingly heterogeneous resources?
That's good. So one way to do it is like, we don't have, for open source models, you can do that. But for proprietary models, you cannot do it. It's hard, right? So that one, you can use a cost as a proxy, right? You can hope that, like for instance, and you can some bounds. So say OpenAI. OpenAI has investment in the future. You know that basically they lose twice as much money as they make, for instance. They make most of the money from inference. So if they lose twice as much than they make, at least it's kind of And, people is not a big cost in this game. It's a 2x, right? But probably even less, right? Because even less, right? It's like, because you need to invest a lot of money for buying more computing for the future. So the cost of per token and so forth, it's a reasonably approximation, right?
Thank you.
Again, it's not perfect. It's a few ballpark.
Hello. Do I have to press something? Oh no, I'm right. I was wondering, does Ray how does it handle interleaving communication and computation, where you have stuff where, you're going to need gradients down the road, but they're not where you want them to be? What do you?
Yeah. I think there are three parts, right? It's like for inference, for instance, obviously you have the parameters, and you have the KV cache. These are the things. For training, you also have activation for the backward pass. So look, it's like in systems, there is no, what you need to do, you need to prefetch and overlap the computation of the current stage, whatever, with prefetching the data for the next stage, right? The key, and ideally you want to have the data before you operate on it. Like for instance, if you do on some kind of pipeline parallelism, when you have a few layers, a few layers of the network, right? You can divide the networks in group of layers, and then when you operate on this group, you try to prefetch for the next group, right? From where? Well, you can do it from the CPU RAM, from another GPU, and things like that. KV cache is the same. It's like you need to. It's about trying to figure out and be efficient in prefetching before. And this will provide limitations, right? Because it's fundamentally, again, it's the overlap between communication and the computation, right? So that's fundamental. It's, right.
Are you using the compute graph to figure out what you're going to need, or are you?
No, that's one layer higher, right? You need to figure out, probably you need another compiler, because to have more knowledge about the particular workload to do it. We tried to do that in the past. It was this other, I don't know, there are other projects like Alpha and doing this. Alpha Serve doing for model parallelism to decompose the models and try to overlap some computation and communication.
Hello, Professor. Thank you for a presentation. I have a question regarding the chatbot arena. So imagine magically we have a benchmark that we uniformly sampling from everyone on Earth. So in comparison with these magical benchmark, how much bias do you think there exists in the current data distribution in chatbot arena?
So there is can be a lot of bias, right? It's again, prompt bias, user bias. You attract a particular kind of users, maybe the one which are more kind of sophisticated users. So it's a lot of bias, but the bias is not concerning if you can account for it, right? Like I mentioned to you, like stylistic, right? Stylist, like if you have a funny answers or more, it's like friendly answers, people will tend to like those more, right? Style over substance. This was your question. But you can account for that also now. Or like position bias, remember. The question is that to identify the bias. Once you identify the bias, you can try to account for the bias and remove, no, if not remove, alleviate the bias, right? So the question, are there bias we are not aware of? And yes, I'm sure there are. But the one we know about it, if you have enough data, you can remove or alleviate at least.
Yeah, quick follow-up question that the chatbot arena is not collecting it. Like it's basically collecting preferences. So I guess there's no of data available to, you know, to do analysis of those bias.
The data which is available, you mean the one which you make it public?
The user background or etc. Say the user background or etc.
It's what?
User background or etc.
We don't have the user background. Right now we don't collect anything about the users. We are going probably to start collecting, but for that we need account.
That would be very
right. If you have accounts now, there are other things you need to delay. GDPR and
Thank
CPA, you. So but we are going to do it.
Okay, it's just pity that we do not have time for more questions. Just let's thank Jan again for the great talk.